In this video, we're going to be applying calculus to solving problems related to kinematics of a particle. And for a very general case, let's consider a particle that is moving along some curve like this. So its displacement is going to be given as x as a function of time. And basically the particle is just going to be moving like this. And we're interested in its position with respect to the x-axis. So basically we know that the transition from this point to that point, that's going to be delta x. So let's call this point x1 and this point x2. And if we want to find the average velocity between those 2 points, we would have an expression like this. So delta x over delta t equals to x2 minus x1 over t2 minus t1. And this is something you would have learned in very early school about in elementary physics classes. But essentially that's the definition of the average velocity between 2 points. In calculus, however, we use another definition that is much better than that, and we call it the instantaneous velocity. So you can imagine that as delta x and delta t both approach zero, they actually approach infinitesimal quantities. So in the end, you end up with the following expression. And the interesting thing about this is that if you know the function that defines the motion of the particle with respect to time, you can simply differentiate it and it will give you a function of the velocity as a function of time. So that's a very neat property about that relationship between velocity and displacement. And usually in mechanics or in dynamics of particles, we denote the derivative of x with respect to time as x dot. Now let's talk about the acceleration. Well, the acceleration is going to have a similar definition, but it is going to be the second derivative of x, which is the same as the derivative of velocity with respect to time. So acceleration is the rate of change of velocity with respect to time, and we can write this as x double dot. So this means first derivative, second derivative with respect to time. And you will see this notation in mechanics used quite a lot. Alright, so what's the relationship between these things? Well, if we graph something like this, let's have an acceleration versus time graph. So let's have an acceleration, and let's call this a constant acceleration a naught. Then that means our velocity, because it's going to be, how do we get from the acceleration to the velocity? Well, if the acceleration is the derivative of v, then it makes sense that to get the velocity in with respect to acceleration, we would just need to integrate the acceleration. So when you have a constant value and you integrate it, what do you end up getting? Well, you get a straight line. You get a function a naught times t plus another constant, and that constant in this case is going to be the initial velocity. Because if you basically plug 0 into here to get the initial velocity, this constant is just going to be that value at time 0. And now what happens if you integrate this? Well, you're going to get the expression for the displacement. So let's have the function for the displacement here. So let's say that it starts from the position 0. So now this curve is going to be defined as at squared over 2 plus v naught t plus the initial displacement, which is going to be x naught. So this is going to be our expression. It's going to be a parabola. So that's basically how you jump back and forth between those three quantities. Now let's solve an example to see how that works. So let's do an example here where we have the following function. So let's say we're given the function acceleration is equal to t squared plus cosine of t plus 3. And we're given the following conditions. The initial velocity of the particle is 2 meters per second, and the initial displacement is 0 meters. So how do we find the velocity? Well, the velocity is going to be equal to x dot, which is equal to the integral of this function with respect to time, and this is going to be equal to t cubed over 3 plus sine of t plus 3t plus a constant c, but we know that this constant c needs actually to be the initial velocity, so that's just going to become 2. And now if we want to get an expression for the displacement of the particle, what we can do is we can have x equals to the integral of the velocity, which is going to be t to the power 4 over 12 plus, sorry, that should be minus cosine of t plus 3t squared over 2 plus 2t plus another constant, which is going to be the initial displacement, and in this case it's 0, so that's going to be your final function for displacement. So just by having the acceleration in terms of t, we found what the displacement was. Now we don't always need to have an explicit function of time. We can have a function of, for example, displacement in terms of velocity, and we can employ the chain rule of differentiation to actually find a solution to that particular problem. So let's consider the general case where we have x written as a function of velocity, which is in itself a function of time. So how do we differentiate this? Well, we know from the chain rule of differentiation that if we want to get the derivative of the x with respect to time, all we need to do is we're going to have dx with respect to v, because function x is an explicit function of v, and then we're going to have dv over dt, and this is the same as writing dx over dv times the acceleration, or x double dot. So let's say we have a function that is defined as x is equal to cosine of the velocity plus sine of velocity. Then what is going to be the derivative of this? Well, dx over dt, which is going to be the velocity, is going to be the following. This is going to be minus sine of v, so that's dx over dv of this function, times dv over dt, because we need to differentiate this with respect to time, so that's going to be dv over dt, and the same applies to this, so that's going to become cosine of v times dv over dt, and we notice immediately that these two terms are actually the acceleration, as we had pointed out before here. So in the end, we're going to get the following: v is equal to minus sine v. Actually, I should write this on the outside, so I'm just going to factorize the x double dot on the outside. That's going to be cosine of v minus sine of v. So you can see that this is going to be an implicit function between velocity and acceleration, and we can actually find a expression for the acceleration of the particle directly in terms of the velocity by simply dividing both sides by cosine v minus sine of v. And if we wanted to get the acceleration in terms of time, well, we can apply the same thing once again, but essentially this is the kind of manipulations you can do with these kind of functions, and you can see that we can apply both integral and differential calculus in many different ways to find relationships between displacement, velocity, and acceleration. So I'll leave this topic here because it's quite broad, and I might make a future playlist on mechanics where I might explain more of the applications of this, but this is the basic idea of how calculus can be applied to fields of mechanics and particles in motion and so forth. And in the next video, what I would like to do is to get started on a concept called multivariable calculus, which is basically taking all of the stuff we have learned so far and taking it further into the third dimension and looking at functions that are functions of more than one variable at a time. So that's when things start to get quite interesting, because we're going to see a lot of connections and a lot of applications of all the knowledge we have acquired so far in this last videos. So in the next video, we're going to start introducing the concept of functions of several variables, and then we're going to see how we can apply calculus in those cases.